So we would like to see where we may be able to capture dark matter. And we have to go to a very quiet space because dark matter interacts so little with us, like listening to a very, very faint sound. And as you might remember from the study of neutrinos in the previous lectures, the best location for that purpose is to go underground because all the noise from the surface and even from outer space get totally shut out. So the underground is an ideal location if you'd like to look for dark matter. And the underground might look like this. This is a picture of a Kamioka mine in Japan when I brought my family together. And you can see, it's a pitch darkness out there. And you have to go drive into this mine and you have a cavity dug inside. And that's where you like to put a very, very sensitive experimental device that you might be able to see this very, very faint interaction of the dark matter particle in that device. And basic idea is very simple. You have an atomic nucleus, and this is the nucleus of your choice. Dark matter particle comes in. It can easily sneak into underground location because it's even less interacting than neutrinos are. And once in a while, you might see this dark matter hitting the atomic nucleus, and the nucleus gets recoiled. And so nucleus all of a sudden receives a little bit of energy, and this energy is something you would like to record in your experimental device. And if you do the math of how much recoil energy the nucleus gets, it really depends on, of course, how fast the dark matter is moving, but also at the same time, what is the mass of the nucleus and what is the mass of our dark matter is. And you can work it out and find that the best case where you get as much energy as possible is when the mass of dark matter and the mass of the nucleus are fairly close to each other. So you'd like to have some idea on what the mass of dark matter is, but as we talked about in the case of WIMPs, something like 300 GeV turns out to be the right mass for dark matter. So then what you'd like to choose is a fairly biggish nucleus, which has, let's say, 200, 300 nucleons, and that would be about the right mass for the best recoil energy in the scattering with dark matter. And the way you detect this recoil energy depends on what kind of experimental techniques you use. Some experiments rely on ionization, some on phonon, some on scintillation, or combination of them. But again, you don't need to worry about what exactly these techniques are for the rest of my lecture here. So this is one such an experiment being built in Kamioka mine in Japan. The name of the experiment is XMASS, XMASS. It has to be built extremely clean to avoid any possible contamination of noise. That's why people wear the clean suits and trying to build this device as cleanly as possible. And they have been completed, and in this device you can put in 1 ton of liquefied xenon, and this is the way you might be able to capture dark matter in an underground location. And this is right now the biggest experiment looking for dark matter detection underground. And this plot is very complicated. Again, you don't need to worry too much about the details. But the point here is this. So this green curve here tells you how much the experiments have probed so far. Horizontal axis is the mass of the dark matter. Vertical axis show how frequently dark matter would interact with the ordinary nuclei. So everything above this line had been excluded experimentally. So that means dark matter should be less interacting than this number for a given mass. On the other hand, what you might expect from certain theoretical models is this region here. So you see that experimental sensitivity is now cutting in to this theoretically expected size of an interaction for a given mass of dark matter. So what it's telling you is that this is actually getting quite interesting. In other words, we might see the report that the dark matter had been detected underground sometime in the next few years. So that's getting pretty exciting. On the other hand, some people think that the waiting for dark matter to be captured underground just takes way too much time. What you're looking for is that placing this sensitive detector underground, you're looking for maybe twice detection in a year. It's a very, very rare thing. So some people get impatient and think about some other ways of finding dark matter. Okay, let's make it. And we have tried to do this with the Higgs boson in the previous lecture. If you put enough energy into empty space, and that energy may be converted to mass of a new particle. So maybe we can possibly make dark matter particle in these particle accelerator experiments such as the LHC. But then you might ask a very good question. Okay, suppose you do make dark matter, but dark matter is not supposed to be seen. So how can you tell that you have produced dark matter at all? Well, the idea is actually fairly simple. You decide if dark matter had been made by a subtraction. So if the beam of the protons in LHC come from your side into the screen, and there's a beam of proton coming from the other side of the screen, and they have the head-on collision right here. And if the collision is head-on, then there shouldn't be any difference between above and below the beam or left and right of the beam. Everything has to be symmetrical around the beam. But if you happen to see an event like this one, then you start wondering something is strange. Because here you see sprays of particles going above, but nothing going below. And that can't possibly be true, because everything has to be balanced in a head-on collision. Everything has to be symmetrical around it. So the only possible conclusion out of this is that, okay, there are particles going upwards. There must be also particles going downwards. But the particles going downwards couldn't be seen. That's why this looks like a huge imbalance between them. Namely that this picture is telling you that they are invisible particles going downwards, carrying away energy and momentum. So this is the way you can tell that something invisible had been created. Basically, summing up everything you can see, and by subtraction, you can tell something is going this way that's invisible. So that's the way you can tell maybe dark matter particles have been created in these particle collision experiments. So the kind of dream we have is this. We have learned from the cosmological measurements by looking at cosmic microwave background, the cluster of galaxies, gravitational lensing effects. We know how much dark matter there should be. That's like a 25% of the entire universe. And because that is determined by how quickly they could have annihilated in the early universe, that is telling you something about its nature, how quickly they can annihilate with each other. If you can find dark matter underground, that tells you how often dark matter would scatter against the ordinary matter. And that also tells you some property of dark matter called scattering cross-section. If you can make them at particle accelerators, you will learn a great more deal about it. You can measure its mass, you can measure its coupling to other particles, and that information then would allow you to compute these things too. In the same way that particle accelerators allowed you to measure how often you can glue protons and neutrons against each other to form nuclei, and that allowed you to predict how much helium could have been synthesized in the Big Bang, and that was contrasted against the astronomical observation, and they turned out to agree with each other. So that's the way we learned how the universe was like when it was only 3 minutes old. I hope you remember that. So in the same way, if you can actually measure the properties of dark matter using particle colliders and make the predictions on how strongly they would interact with the ordinary matter, how much of them should be left over to the current universe, and if that agrees with what we observed in cosmological measurements, only then we can claim that we have a victory, namely we have understood what dark matter particle is, but also at the same time we have understood how the universe was like when the dark matter was created, and that actually turns out to be this era of the universe. Universe was only like a 10 billionth of a second old. So that way, we hope to go well beyond the 3-minute-old universe where the helium had been synthesized back to the point where the dark matter had been made. So this is how we would like to make a progress in understanding towards the beginning of the universe. Okay, the next question is the antimatter. What do you know about antimatter?